Today we're going to talk about the triple only content in C2 Part 2 Organic Chemistry. Now you should see here that there are quite a lot of triple only topics in this section. We take our knowledge of alkenes slightly further by talking about the reactions of alkenes, and then we talk about carboxylic acids, alcohols, and begin to talk about esters. Now, let's move on to looking specifically about the extra detail we need about alkenes. Now, in the last video, we talked about alkenes. We talked about how the functional group for the alkene homologous series is C-double-bond-C. You need to know all of that knowledge, obviously, but we need to take it slightly further now when we talk about alkenes for the triple science papers. So you need to know about 3 reactions, and I have got the names of them here: hydrogenation, hydration, and halogenation. Now, you don't need to know the names specifically, but the fact that they're the triple H might help remember it. So firstly, I've drawn these with their display formulas, and I've done that so that you can see very clearly that they react across this double bond. Because what I have done here is draw for you the alkenes and the other reagent, and then shown you what they look like. Here you've got ethene, which only has one carbon-carbon bond regardless. Now, if we had propene, it's important to note, or butene, or pentene, etc., that this addition reaction would still happen across the double bond. So these are all addition reactions. The first one we've already talked about is that bromine water reaction. I haven't drawn it out here because we looked at it in the last video. Now we can turn an alkene into an alkane via a process called hydrogenation, where we react it with hydrogen, and that hydrogen is added across this double bond, so you make the alkane. So if we start with ethene, we make ethane. We then have hydration. Now, hydration, you should hopefully think about water regardless when you hear the word hydration. That's exactly what's happening here. You have ethene, and we add H2O across there, which is 2 lots of hydrogens and an oxygen. Now, what you should remember is when you look at water, actually, water dissociates into OH and H, and so that's the 2 groups that are added. So what you see is that we open up this bond again, and that you have OH attaching to one carbon and hydrogen attaching to the other. And this is an alcohol. And we can tell it's an alcohol because it's saturated and it has this OH group on there. So this is ethene, this would be ethanol. And this is a really important reaction here. And we talked about cracking in the last video and about why it's so important that we make alkenes. Partly it's because alkenes can be used for a number of things to make things like ethanol. And ethanol is an important industrial solvent. It can be used as a fuel. So this is another route to making ethanol. And the last one that you need to know about is halogenation. And it's literally, again, just adding a halogen across that double bond. So you start with your ethene, you add your chlorine, your iodine, your bromine, whatever you want here. And then you make your dichloroethane. Okay, dichloro because there are 2 chlorines, and ethane because this is now saturated. There's no longer the double bond. So that's the name of the molecule. So those are the reactions of alkenes. Now that, with everything you've learned previously about alkenes, is everything you need to know for that section. Now, we're going to move on now to our next functional group. And our next functional group our next homologous series is the alcohols. Now, alcohols are a family of chemicals, a homologous series. They are not simply just ethanol, and that's what we more commonly think of when we hear the word alcohol. Now, I've written the general formula here, but strictly we don't need to know this. The big thing here is an alcohol, when you draw the structure, you basically want to draw the structure of the alkane and then add an OH instead of one of the hydrogens. So rather than +2, which is the general formula for an alkane, it's +1 and then an OH group. We name alcohols with the ol at the end. So a alcohol that has 1 carbon would be methanol. Now, the functional group of the alcohol is OH, okay? And that's what makes it an alcohol. So if you see OH there, then that is an alcohol. And those are all the key points there. Now, before we move on to some more difficult chemistry, what I'd like to do is have a go at writing the formulas for alcohols. So what I want you to do now is pause the video, look at what I've got up here as your general formula for alcohols, what you know about what the M, E, P, and B stand for, and have a go at writing those formulas. As an additional thing that either might be easier or more difficult depending on what level you're at, have a go at writing the display formulas, and that means showing all of the bonds. Pause the video now and have a go at that. Okay, so what you should have had is this here. You have CH3OH for methanol, C2H5OH for ethanol, C3H7OH for propanol, C4H9OH for butanol. Now, just another point here, it is good practice to write the OH group, the functional group, separately at the end. You could just pop your hydrogen here because that would give you your molecular formula. That would be fine, but we normally will write the functional group separate at the end. Now, other features of alcohols. Their solubility decreases with chain length. Now, you might think that some alcohols display the properties of oil when they mix with water. They are what we call immiscible, okay? But actually, your very short molecules, your methanol and ethanol, they do dissolve in water fine, but that decreases with chain length. So the larger alcohols, they become less soluble. Now, one thing that the example do want you to know is about one method of formation of ethanol. And actually, this is the formation of something we call bioethanol. And that's through the process of fermentation. Now, you will have seen this already when you have looked at anaerobic respiration. And when we look at the anaerobic respiration of yeast, this is exactly what we're talking about. So here you have the fermentation of glucose forming ethanol and carbon dioxide. It's anaerobic respiration of glucose to form ethanol and CO2. And this takes place in yeast. And what the example would like you to know is they would like you to be able to identify those conditions. And I've just taken these from online just to show you. So you have yeast and you have sugar that is dissolved in water, and that enables the sugars to be accessed more easily by the yeast. An airlock to allow carbon dioxide out as it is produced, but stopping air getting in. This is really important because if air gets in, then oxygen gets in. And then what you might have is a situation where instead of doing the anaerobic respiration, the fermentation that you want to, you might begin to do aerobic respiration, which will not give you ethanol. And lastly, you want a warm temperature. Yeast is a microorganism, it is a fungus, it is alive. And so you want a warm temperature so the enzymes within that yeast can work adequately and at an optimum level. So that is fermentation. That's how we form bioethanol. And obviously, we looked earlier, we could see that hydration is another method of making ethanol, or any alcohol, I should say. Now, the next thing we need to look at is the reactions of alcohols. And there are three that we need to look at. The first one I want to show you is the oxidation of an alcohol. Now, in the oxidation of an alcohol, we react ethanol or any alcohol with an oxidizing agent to form ethanoic acid and water. Now, in general, this means that oxidation of an alcohol gives you a carboxylic acid. Now, I have given you this formula rather than ask you to have a go at it because this here is the shorthand way of writing oxidizing agent. And the reason we write this here is because actually you can use quite a few different oxidizing agents. An oxidizing agent is something that will oxidize the thing it reacts with whilst itself being reduced. So it will oxidize the ethanol really nicely to form this carboxylic acid. And that makes sense because if you look at the structure here, what you see is that the carboxylic acid has got an extra oxygen. It's a C-double-bond-O, and we'll look at carboxylic acids in a minute. And then we make water. So that is the reaction, the oxidation of ethanol, okay? Now, in the real world, this makes sense. If you have a bottle of wine, not that I expect you personally will have a bottle of wine, and you leave the lid off or you leave it uncovered over a period of time, that wine will begin to taste vinegary. And the reason it does that is because ethanoic acid is being formed through oxidation, and ethanoic acid is vinegar. So that's the explanation for that. Let's now move on to looking at combustion. Now, combustion of alcohols is really, really important. One of the main uses of ethanol in industry, obviously we know that it's used as a beverage, we know that it's used as an industrial solvent, as are most of the alcohols, but another really important use of alcohols is as a method of fuel. And actually, if we can use biomethods to produce ethanol, then it is a more sustainable fuel to use. So in the combustion of ethanol, we make carbon dioxide and water as we do with any complete combustion. Now, what I would like you to do now to get good practice is I would like you to pause this video and I would like you to have a go at writing out the equation, the symbol, balanced symbol equation for this reaction. Give yourself a couple of minutes to do that. Pause the video now, and then we'll come back with the answer. So, the balanced symbol equation here is we have C2H5OH as your formula for ethanol. That reacts with 3 lots of oxygen, and then that gives us 2 lots of carbon dioxide and 3 lots of water. Really important things to note. These small letters must all be just that. Sorry, these small numbers, they must all just be that. They must be subscripts. They must be small and to the bottom of the letters. These must be large. That's one way that you will lose your mark. In an exam, if they ask for the balanced symbol equation, you must do both for full marks. Now, your next reaction of alcohols that you need to know is that it reacts with sodium. And actually, it can react with other metals as well, but sodium is the one they specifically want you to look at. Now, sodium is in group 1, and it reacts with ethanol to form sodium ethoxide and hydrogen. Now, you might be thinking, why have you asked me to do this? I don't know what an ethoxide is. Well, what I need you to think about here is that you're reacting sodium, which is group 1, which is Na+, with an alcohol, which has a functional group of OH. Simply, that sodium and hydrogen can switch places. You know you're producing hydrogen, so you'll be making H2 at the end. So sodium ethoxide looks very similar to an alcohol, just without that H on the OH. Have a go at doing the balanced symbol equation for this, and then we'll go through this after you've paused it in just a second. So let's have a go at this. We've got 2 lots of sodium reacting with 2 lots of ethanol to give us C2H5ONA. So just as I said before, that hydrogen is replaced by a sodium to give us ONA, the ethoxide, okay? And hydrogen at the end. And because we've got that H2, we need 2 lots of the alcohol and everything else. So those are the reactions of the alcohols. Now that is alcohols in general. If you need to come back to pause it and go back over this so you've got good notes, please do feel free. Now we're going to move on to carboxylic acids. Now, carboxylic acids are acids like any other. They are weak acids because they only partially ionized in solution, which means that only some of the hydrogen ions are dissociated. And they react as other acids would. So they react with alkalis, they react with metals, they react with carbonates. The salt that carboxylic acids form take the form of OH. So if you are making a salt with ethanoic acid, it would become an ethanoate. With propanoic acid, it would become a propanoate, etc. Now here, your formula for carboxylic acids are always contain the functional group COOH. And that C adds to your total number of carbons. Now, sorry. Now, COOH is always at the end. And then you need to add on whatever comes before it. So, for example, if we were looking at methanol, we would say, right, methanol only has 1 carbon, and that carbon's already there. Now, COOH looks just like this down here. It's got a double bond to the oxygen, a single bond to the OH. And that means it can make 1 more bond. So the formula of methanoic acid is simply HCOOH. Now, as you go up to the carboxylic acids with more carbons, you literally are adding a CH2 group each time. So if I were going to do the formula for ethanoic acid, I could start by drawing my functional group because that's going to help me. Now I know that ethanoic acid has 2 carbons, so I'm going to draw another carbon just here, and then I'm going to add my hydrogens. Now this carbon is making the amount of bonds that it can do, so this carbon's only making 1. I know it can make 4, so I'm going to fill in with the rest of my hydrogens, and that would mean that this is the formula for ethanoic acid. And then if I were going to write it out as a formula, I would literally count what I've got. Remember that we do like to keep the functional group at the end separately. So write down what you've got here and then write down your functional group afterwards. What I would like to do now is have a go at working out the display formulas for the first 4 carboxylic acids. So write down the display formula if you want to, but then next to it, write down the molecular formula so that you have that there. You can write structural formula if you prefer, which is where you write what's happening at each carbon separately. Pause the video now and have a go. So here is your answer. If you were going to draw them separately, if you were going to write them as your molecular formula, this is what you would do. Now, if you were going to write it in the structural formula way, this ethanol would be the same and methanol would be the same. What you could do with things like propanoic acid, sorry, these acids, not ethanol, not alcohols, propanoic acid, you could just write what's happening at each carbon. CH3, CH2, COOH is also fine. For butanol, CH3, CH2, CH2, COOH. Like I said before, we get bigger by CH2 each time. So that's the formulas of your carboxylic acids. Okay, so now let's look at some other key things about them. So first of all, the key thing here, as I've said before, is that these are acids, they react as acids, but they are weak acids because they are only partially dissociated. That means they react in many of the other ways that normal acids do. And you have that information because that's things that you've covered previously. But the specific reaction that you need to know of the carboxylic acids is their reaction to make esters. Now, esters have a functional group of COO, and you'll see that I have written on either side a dash to show that they bond to either side of this. This is in the middle of the molecule. Now, esters are made by reacting alcohol and carboxylic acids. Now, those who are more eagle-eyed will realize that this looks very similar to a condensation reaction, and it's exactly what it is. This is the same initial reaction that you would have in a condensation polymerization. So what happens? Well, here you've got your alcohol, and here you have got your carboxylic acid. In this reaction, water is formed. And so what we do is we take a hydrogen from the alcohol and we react that with the OH on the carboxylic acid. And that forms water. What we're left with is CO, and that O bonds to where you took the OH off, because that is now going to be very reactive if the OH is not there. So this oxygen will bond into this carbon just here. And so what you're left with is your alcohol bit first here with your ester linkage, that's what we want to call it. And then your C double bond O, this is your ethanoic acid part, or your carboxylic acid part, I should say. Now, the naming of esters is in the form something with YL at the end and then something with OAT at the end afterwards. Now, the first part of the name of the ester comes from the alcohol, and the second part comes from the carboxylic acid. So even if you can't work out what the display formula would be for the product, you can name it. So alcohol, in this case, is ethanol because we've got 2 carbons, and the carboxylic acid in this part is propanoic acid because we've got 3 carbons. And so the name of your ester would be ethyl propanoate. Now that is everything you need to know for the triple science section of the organic chemistry in C2. Now this does very, very heavily link on to your polymers section, which again is triple science only for the organic part of that, which will be in a separate video as it's a little bit more complicated. Feel free to rewatch this video to give yourself some more information to make additional notes if necessary.